All right, so we are going to do the Unit 11 review. So this is all stoichiometry, right? So one of the most important things about stoichiometry is having a balanced equation. So for this first one, we currently have an equation, but it's not a balanced equation. So we need to balance it. Now, we're going to start by balancing the c. So we have two c's on the left. We have one c on the right. So we can fix that by putting a 2 there. Okay. We are going to save balancing the oxygens for last because the oxygen is in two different places. So we can balance the H's next. Okay. We have 6 H's over here. We have 2 over here. So we can put a 3 here. Okay. Now, here's where the problem comes in. Okay. We have right now 4 O's here and we have 3 O's here. So we have a total of 7 O's. Okay. Now, that's bad, right? Because there's no number we can put here to balance out the oxygens. Okay. So, because it's an odd number on the right side and we can't get an odd number on the left side. So, what we need to do here is to get rid of an odd number, we need to multiply by 2, right? If we multiply 7 by 2, it's not an odd number anymore. So to get there, we're going to just put a 2 in front of this very first thing that we were balancing, okay? Now, because of that, we're going to erase all this stuff, okay, because that's going to change all that stuff. So now, instead of having 2 C's here, we have 4 C's, so we'll put a 4 there. Instead of having 6 H's, we have 12 H's. So we'll put a 6 there. So we have 12 H's over there. So now we have 8 O's here, and we have 6 O's here. So that's a total of 14 O's. So now we can put a 7 here, and now it's balanced. Hooray! So now we have a balanced equation. Now we can start doing our actual conversions, okay? So first one, how many moles of CO2 are used when 16.54 moles of carbon dioxide are produced? So in any conversion problem, we start with our given. So our given is 16.54 moles of carbon dioxide, which is CO2. We put that over 1, okay? We do our conversion factor. Moles of CO2 is what we want to cancel out. So we need to put that on the bottom. Moles CO2. Okay. We are converting to moles of C2H6. So we want moles of C2H6 on the top. Now, since we have our conversion factor with moles on top and moles on bottom, that means this is our mole ratio. So for our mole ratio, we use the coefficients for our equation, which is why it's important to have a balanced equation. Okay, so our coefficient for C2H6 is 2. Our coefficient for CO2 is 4. Okay, moles of CO2 cancel out. We're left with moles of C2H6, which is where we want to be. So now we're done with our conversion factors. So now we just do our math. We do 16.54 times 2 divided by 4, and we get 8.27 moles of C2H6. All right, so next, how many moles of O2 are needed to react with 5.4 moles of C2H6? Okay, so same situation. We start out with our given. 5.47 moles C2H6. We put that over 1. We do our conversion factor. Moles of C2H6 is going to go on the bottom. There we go. We want to go to moles of O2. So we put moles O2 on top. We have moles on top and moles on bottom, which means this is our mole ratio. So we need our coefficients. Coefficient for O is 7. Coefficient for C2H6 is 2. So same situation, 5.47 times 7 divided by 2 equals 19.1 moles of O2. Good. All right, so this one, it already gives you a balanced equation, so we don't have to worry about that. Okay, so how many moles of NH3 will be produced when 8.94 moles of H2 are produced according to the following reaction? So again, we start with our given, 8.94 moles H2O. We put that over 1. We do our conversion factor, moles H2O. We are converting to moles of NH3, so moles of NH3 goes on top. We have moles on top and moles on bottom. That means this is our mole ratio. So our coefficient of H2O is 3, right there. Our coefficient of NH3 is 6, right there. Okay, moles of H2O cancel out. We're left with moles of NH3, which is where we want to be. So now we just do our math. 8.94 times 6 divided by 3, and we get 19.1 moles of N. Oh, wait, sorry. No, that was the last one. My fault. We get 17. 17.9 moles of NH3. There we go. That's what we get. Okay? Good. All right, so using the equation from question 1, how many grams of oxygen gas are needed to make 8.640 grams of water? So now it gets a little bit more complicated. We're not just going from moles to moles. It's not just going to be the mole ratio. We have to convert from grams of water to moles of water to moles of oxygen to grams of oxygen. Okay, so we start with our given, 8.640 grams of water over 1. We do our conversion factor. Okay, we do grams of H2O on the bottom because we want to cancel that out. All right, now our end goal is grams of oxygen. Now, we cannot go right from grams of H2O to grams of oxygen. We can convert grams of H2O to moles of H2O. Okay. Now, anytime we have moles on top and anything other than moles on bottom, 1 goes in front of moles. What goes in front of grams, we always put the molar mass. So the molar mass of H2O is 18.016. Okay, grams of H2O cancel out. We're left with moles of H2O. That is not where we want to be. We want to be at grams of oxygen. So we need another conversion factor. We can't stop yet. All right, so now we have moles of H2O. We want to cancel that out. So we put moles H2O on bottom. We cannot go from moles of H2O to grams of oxygen. You can't go from moles of one thing to grams of a different thing, but we can go from moles of H2O to moles of O2. Okay. Now, again, we have moles on top, moles on bottom. That's our our mole ratio. So we look up here. We find our coefficients for oxygen and water. Oxygen is 7, water is 6. So we put those there. Moles of H2O cancel out. We're left with moles of O2. That, again, is not where we want to be. We want to be at grams of O2. So we need another conversion factor. We want to cancel out moles of O2. We can go from moles of O2 to grams of O2. So we put grams of O2 on top. Again, if we have moles on bottom and anything other than moles on top, then 1 goes in front of moles. The molar mass always goes in front of grams. So that's going to be 32 because oxygen is 16 multiplied by 2 is 32. Moles of O2 cancel out. We're left with grams of O2. That is where we want to be. So that means we do not need any more conversion factors. All right, so now we're going to multiply all of our top numbers. We're going to get an answer. Multiply all of our bottom numbers, get an answer. We're going to take our top number, divide it by our bottom number, and that is going to give us 17.92 grams of O2. Okay? All right, continuing along. How many liters of oxygen at STP are needed to make 32.14 moles of carbon? So, our given 32.14 moles of carbon. I'm sorry, carbon dioxide. 32.14 moles CO2 over 1. We do our conversion factor. We want to cancel out moles of CO2. So moles CO2. We cannot go from moles of CO2 directly to liters of oxygen, but we can go to moles of oxygen. We have moles on top and moles on bottom. So we're looking for our coefficients of O2 and CO2. So we scroll up. O2 is 7, CO2 is 4. So O2 7, CO2 4. Moles of CO2 cancel out. We're left with moles of O2. That is not where we want to be. So we need another conversion factor. We want to cancel out moles of O2. We can go from moles of O2 to liters of O2. So we put liters of O2 on top. Moles on bottom, not moles on top, means 1 in front of moles. The number that goes in front of liters is always going to be 22.4. Moles of O2 cancel out. We're left with liters of O2. That is where we want to be. So now we can do our math. So we're going to take our top numbers divided by our bottom numbers, and we are going to get 1,259.8 liters of O2. Okay? All right. So now we're going to need a balanced equation, which I'm going to do down here so I can scroll down a little bit when we actually have it. For ammonium sulfide reacts with copper 2 nitrate in a double replacement reaction to produce ammonium nitrate and copper 2 sulfide. All right, so ammonium sulfide. Ammonium, you would find on the charge chart. It is NH4 plus 1. Sulfide is S minus 2. So you put those together, balance them out, you get a formula of NH4 parentheses 2S plus copper 2 nitrate. So copper is Cu plus 2 because it has a Roman numeral 2. Nitrate, you would find that on the charge chart. It is NO3 minus 1. So to balance out those charges, it would be Cu NO3 parentheses 2. That yields ammonium nitrate. Ammonium is still NH4 plus 1. Nitrate is still NO3 minus 1. So we get NH4, NO3 plus copper 2 sulfide. So copper 2 is still Cu plus 2. Sulfide is still S minus 2. So that's going to give us CuS. Okay? All right, so now we need to balance that. So all we need to do to balance this is we have 2 NH4s over here. We have 1 over here. So we put a 2 in front of that. That gives us that balances out our NH4s. That also increases our NO3s, which we needed 2 of those anyway. So that's all we need to do for that one. Hooray! All right, so how many moles of ammonium nitrate are produced from 5.22 grams of ammonium sulfide? So we start with our given as usual, 5.22 grams ammonium sulfide. So that is NH3, 4, NH4, 2S over 1. We do our conversion factor. Grams, NH4, 2S goes on bottom. We cannot go from that to moles of ammonium nitrate, but we can go to moles of NH4, 2S. Moles on top, not moles on bottom. That means there's a 1. Grams, what goes in front of grams every time is the molar mass. So that is 68.17. Grams of that cancels out. We're left with moles of that. That is not where we want to be. So we need another conversion factor. Moles of that on bottom. Oh, not that. Moles of that on bottom. We can convert from moles of that to moles of ammonium nitrate. So we put moles ammonium nitrate on top. So now, since we have moles on top and moles on bottom, that means that is our mole ratio. So our mole ratio is going to be our coefficients. So NH4 to S, the coefficient is a 1. NH4 NO3, there it is. The coefficient is a 2. Moles of that cancels out. We're left with moles of NH4NO3, which is where we want to be. So no more conversion factors. So now we just do our math. So we multiply all our top numbers together, multiply all our bottom numbers together, we divide, and we get 0.15 moles of NH4 NO3. All right, next, how many grams of copper 2 sulfide are produced along with 13.88 grams of ammonium nitrate? So we start with our given. Ooh, I should probably, there we go. Now we can see the form or the equation. 13.88 grams of NH4NO3. Put that over 1. We do our conversion factor. We are looking for grams of copper 2 sulfide. Okay. So that's going to be that. All right. So grams of NH4 NO3 goes on bottom. We cannot go from that to grams of copper 2 sulfide, but we can go to moles of NH4 NO3. Moles on top, not moles on bottom. So that's a 1. Grams, we put the molar mass. So that's 80.06. Grams of that cancel out. We're left with moles of that. That is not where we want to be. So we do another conversion factor. Moles of that on bottom to cancel out. We cannot go from moles of that to grams of copper 2 sulfide, but we can go to moles of copper 2 sulfide. Okay, moles on top, moles on bottom. That means that's our coefficient. So the coefficient of that is 1. The coefficient of that is 2. Moles of that cancel out. Moles of CuS are not where we want to be. So we need another conversion factor. We need moles CuS on bottom. We can convert moles of CuS to grams of CuS. So we put that on top. Moles on bottom, not moles on top. So we need a 1 in front of moles. we need molar mass in front of grams, so that's 95.61. Moles of CuS cancel out. We're left with grams of CuS. That is where we want to be. So we do our math, and we get 8.29 grams CuS. All right, so next, limiting reactant and theoretical yields. So first, we need to write out our balanced equation, okay? Nitrogen, which is N2, because it's diatomic, reacts with magnesium, which is Mg, to produce magnesium nitride. So magnesium, which is +2, nitride, which is -3. If we balance those out, we're going to need 3 magnesiums and 2 nitrogens. So that is going to work out to be Mg3N2. Okay? Okay, so now we need to balance it. We have 2 N's. 2 N's, that's good. We have 3 Mg's. We have 1 Mg. That's not good, but we can just put a 3 there, and now it's good. All right, what is the theoretical yield when 5 grams of magnesium is reacted to a 25 grams of nitrogen gas? So the way that theoretical yield problems work and limiting reactant problems work is basically you just need to do 2 stoichiometry problems. One with that given, and a separate one with that given. So we'll start with our 5.0. So 5.00 grams of magnesium. And we're converting to our product. Okay, now in this case, we only have one product. Okay, so we're going to convert to that. If there were 2 products, then you have there are 2 possibilities here. If it's asking for what is the theoretical yield of one of those 2 products, you convert to that product. If it doesn't specify, it just says what's the limiting reactant, then you can convert to either of the 2 products, but you have to convert to the same product for both of your problems. Okay? So we put our first given over 1. We do our conversion factor. Grams of magnesium goes on bottom. Moles of magnesium goes on top. 1 in front of moles. The molar mass of magnesium in front of grams, which is 24.31. Grams of Mg cancel out. We're left with moles of Mg. That's not where we want to be, so we need another conversion factor. Moles Mg on bottom. We want to go to grams of Mg3N2. We can't go directly there, so we're going to put moles of Mg3N2 on top. That is our, oh shoot, oh there it is, duh. That is our mole ratio, so we need our coefficients. Coefficient of Mg is 3. Coefficient of Mg3N2 is 1. Moles of Mg cancel out. We're left with moles of Mg3 and 2. That's not where we want to be, so another conversion factor. Moles Mg3N2 on bottom. Grams Mg3N2 on top. 1 in front of moles. Molar mass in front of grams, and that turns out to be 100.95. Moles cancel out. Left with grams. That is where we want to be. So now we do our math, and we get 6.92 grams Mg N2. All right, so we're halfway done. Now we do the same thing for our other given. 25.0 grams of N2. We put that over 1. We do our first conversion factor. Grams N2. Moles N2 on top. Molar mass of N2 is 28.02. Moles is 1. Grams cancel out. We're left with moles. That's not where we want to be. So we do another conversion factor. Moles N2 on bottom. Moles mg3 N2 on top. So now we use our conversion or our coefficients. N2 is 1. Mg3 N2 is also 1. Moles of N2 cancel out. Moles of Mg3 N2 are left. That's not where we want to be. So moles Mg N2 on bottom. Grams Mg N2 on top. 1 goes next to moles. Molar mass goes next to grams. 100.95. Moles cancel out. We're left with grams. That is where we want to be. So now we do our math. And we get 90.07 grams of MgN2. Oh, I'm sorry, Mg3N2. Okay, so now our math for this one is done. But we're not done with the problem yet. Okay, so what both of these are the maximum amount of product that can be produced given these two starting points. Okay, so what this means, if we have 5 grams of magnesium, the most magnesium nitride we can make is 6.92 grams. If we are given 25 grams of N2, the most magnesium nitrate we can make is 90.07. So what that means is if we're given both of these amounts, we are going to run out of the magnesium first because we can only make 6.92 grams of magnesium nitride with 5 grams of magnesium. So after we get to 6.92 grams of magnesium nitride, oh, that should be a 3 there, sorry. Then we're done with the reaction. We can't make the 90.07 because after we get to 6.92, the reaction stops. So that means 5.0 grams is our limiting reactant, and 6.92 grams of magnesium nitride is our theoretical yield. Okay? So again, that's very important. 6.92 grams of magnesium nitride is not the limiting reactant. Okay? If the question is asking for the limiting reactant, it's going to be one of your givens, not the answer that you come up with. Okay? Okay, awesome. So, moving along. All right, sorry for that pause. My headset just died for some reason. Okay. A large amount of heat is generated by the following reactions. So the water produced from the reaction, blah, blah. We don't need to read all this. What is the percent yield if 155 grams of calcium carbonate is treated with 250 grams of anhydrous hydrogen chloride and only 142.0 grams of calcium chloride is obtained? Okay, so this is kind of tricky because there's a lot of numbers here, right? So it's asking for the percent yield. Now, in order to find the percent yield, you have to identify the actual yield. Okay, so the actual yield is going to be this 142. Okay, because it says only 142 grams of calcium chloride is obtained. So that means like if we did this in a lab and actually mixed all the stuff together and then collected the product, we would be able to we would collect 142 grams of calcium chloride. So that is our actual yield. Okay, so we're not going to use that until the end. Now, this 155 and this 250, those are our two givens. So we're going to do two different stoichiometry problems with those. So we're going to start with the 155 grams of calcium carbonate. All right, so we need grams, CaCO3 on bottom, moles, CaCO3 on top. Moles, there we go. 1 mole, molar mass in front of grams, so that's 100.09. Grams cancel out. We're left with moles of COC3. That's not where we want to be. So we do moles CaCO3 on bottom, moles of, what are we looking for? I forgot. Calcium chloride. So the reason why we're doing calcium chloride and not H2O is because calcium chloride is what our actual yield is in. So we need to convert to grams of calcium chloride. Okay, so to do that, we need to first convert to moles of calcium chloride. So moles, CaCl2. This is our molar mass. I'm sorry, mole ratio. So we use our coefficients, which is 1 and 1. Moles of that cancels out. Moles of this is left. That's not where we want to be. So we do another conversion factor. Moles CaCl2 is on the bottom. Grams CaCl2 is on the top. 1 goes in front of moles. Excuse me. Molar mass goes in front of grams. So 110.98. Moles cancel out. We're left with grams. That is where we want to be. So we do our math, and that comes out to 171.8 grams CaCl2. Okay. All right, so now we do the same thing with our other given, which is 250 grams of hydrogen chloride. So that's HCl over 1. We do our conversion factors. Grams HCl on bottom, moles HCl on top. 1 next to moles, molar mass next to grams, which is 36.46. Grams HCl cancels out. We're left with moles HCl. That's not where we want to be. Moles HCl on bottom, moles calcium chloride on top. 2 next, or this is moles and moles, so this is our coefficients. Coefficient of HCl is 2, coefficient of CaCl is 1. Moles of HCl cancels out. We're left with moles of CaCl2. That's not where we want to be. Moles CaCl2 goes on bottom. Grams CaCl2 goes on top. 1 goes next to moles. Molar mass goes next to grams, which is 110.98. Moles of that cancels out. Grams of that is left, which is where we want to be. So we do our math, and that turns out to be 380.48 grams of CaCl2. Okay, so now we are comparing our two yields. Okay, whichever one is the lower one is our theoretical yield. So that means that this is our theoretical yield. Now, from here, we are going to, since this is the maximum amount we can possibly make, and this, our actual yield, is what we actually got, to figure out our percent yield, we just take our actual yield divided by our theoretical yield times 100. So we're going to do 142 grams over 171.8 grams times 100, and that gives us a percentage of 82.6%. And there we go. That's it for that. All right, so next, we're going to balance this equation. All right, so we're going to start off with our F's, right here. We have 6 F's over here. We have 1 F over here. So we're going to put a 6 in front of that to balance that out. Okay, we're going to save H's for last because H's are in 2 different places. So now we can look at the SIs. SIs are already balanced, and we can look at our oxygens. We have 2 oxygens over here. We have 1 oxygen over here. So we can put a 2 there. Okay, and from there we have 4 hydrogens here, 2 more hydrogens here, so that's 6 total, and we have 6 hydrogens here. So we're balanced. Hooray! All right, so now, what is the theoretical yield in grams of that produced when 40 grams of that are mixed with 40 grams of that? So, same situation. We're going to do 2 stoichiometry problems. So, 40 grams of silicon dioxide over 1. We do our conversion factor. Grams of SiO2 goes on bottom. Moles of SiO2 goes on top. 1 next to moles, molar mass next to grams. Grams cancel out. We're left with moles. That's not where we want to be. Next, moles of SiO2 on bottom. We are looking for the theoretical yield of hexafluorosilane, blah, blah, whatever, which is H2SiF6. Okay, so that is what we are converting to. Okay, so moles of H2SiF6. Okay, we have moles on top, moles on bottom. That means this is our mole to mole ratio. So coefficients. Moles of that cancel out. Moles of this is where we are, which is not where we want to be. So another conversion factor. Moles of that on bottom. Grams of that on top. 1 next to moles. Molar mass next to grams. Moles of that cancel out. Grams of that are left. That is where we want to be. So we do our math, and that is 95.9 grams. Same thing with our other given. That one, 40 grams of hydrofluoric acid. So that's HF. We do our conversion factor. Grams HF on bottom. Moles HF on top. 1 next to moles. Molar mass next to grams. Grams cancel out. We're left with moles. That's not where we want to be. So moles of HF on bottom. Moles H2Si. Oop, that should be an I, not a, oh, I don't know, whatever it is. SiF6 on top. 1 coefficient for that. 6 coefficient for that. Moles of HF cancel out. Moles of that is left. That's not where we want to be. So moles of that on top. Grams of that moles of that on bottom and grams of that on top. 1 next to moles. Molar mass next to grams. Moles cancel out. We're left with grams. That is where we want to be. And we get 48.01 grams. Ooh, and I forgot to put the unit here. H2SiF6. H2SiF6. Okay, so now our lower one is our theoretical yield. So that's going to be this one. That is the maximum amount that we can make, which means our limiting reactant is the reactant that produced that theoretical yield. So our limiting reactant is going to be 40 grams of HF, because HF is the one that produced our theoretical yield. All right, so now if 45.8 grams of hexa blah, blah, blah are actually produced, what is the percent yield? So for percent yield, we take actual yield, which is this, because that's what actually is produced, divided by theoretical yield times 100. So 45.8 grams divided by 48.01 grams times 100 equals 95.4%. That's an excellent percent yield. Hooray. Okay. So next is this next one, which makes sense. All right, so first off, we need our equation. Methyl alcohol is made by reacting carbon monoxide with H2. Okay, so carbon monoxide, which is CO, plus H2, which is H2, obviously. And that produces methyl alcohol, which it gives you the formula for right up there, CH3OH. All right, so now we got to balance. This is super easy to balance. C, one C over here, one C over here, one O here, one O here, two H's here, four H's here. So we just need a 2 right there. Okay, so now we do our equations. If we start with 2.5 grams of H2 and 30 liters of CO. So those are our two givens. So we'll start with 2.5 grams H2 over 1. Do our conversion factor. Grams H2 on bottom, moles H2 on top, 1 next to moles, molar mass next to grams. Grams cancel out. We're left with moles of H2, not where we want to be. Moles of H2 on bottom, moles of methyl alcohol on top. So that's our coefficients. So 2 next to H2, 1 next to that. Moles cancel out. That's not where we want to be. Moles on bottom, CH3OH. Grams on top, CH3OH. 1 next to grams. Molar mass, 1 next to moles. Molar mass next to grams, 2.05. Moles cancel out. We're left with grams. That is where we want to be. So now we just do our math. And that turns out to be 42.92 grams CH3OH. Okay, so now I'm not sure if well, I'll just do it down here. That's fine. All right, so our next one is 30.0 liters of CO. All right, so we do our conversion factor. We need liters of CO on bottom, moles of CO on top. 1 goes next to moles. 22.4. Ooh, I just realized I was looking at the wrong answer up here. So rewind. So that was not right. I was looking at the wrong one. That should be 19.8 grams. Okay, that 42.92, that's going to be the answer to the one we're doing right now. So sorry about that. Okay, so liters of CO cancels out. We're left with moles of CO. That's not where we want to be. So moles of CO goes on bottom. Moles of alcohol goes on top. Moles on top, moles on bottom. So that's our coefficient, which is 1 and 1. Moles of CO cancels out. We're left with that. That's not where we want to be. So moles CH3OH. Grams CH3OH. 1 next to moles. Molar mass next to grams. Moles cancel out. We're left with grams. That is where we want to be. And now that's where we get our 42.92 2 grams of CH3OH. Whoops. There we go. That's a really bad H, but you guys get the picture. Okay. So now the lower of the two is our theoretical yield. So that's this one right here. Okay. So that's our theoretical yield, which means the 2.5 grams of H2 is our limiting reactant. Okay. So 2.5 grams of H2 is our limiting reactant. Our theoretical yield, like we said, is 19.8 grams CH3OH. And that's it for that one. Okay, so next is this one. Now I do have this, the other product is NaNO3 that is on your review, but at the time of me making this video, I didn't have it on here, so I did update that, so this should be on there. Excuse me. Okay, in a reaction of 15.3, actually, we're just gonna. So first, we have to do our reaction, our equation. So NaCl is one of our products. So Na, we'll do it right here. NaCl reacts with PbNO32 to yield lead 2 chloride. So that's Pb plus 2 Cl minus 1. So that means our formula is PbCl2. And our other product is NaNO3. Okay? Okay, so there's our equation. Probably need our numbers too. So in that reaction, we have 15.3 grams of NaCl. NaCl, and we want to find out how many grams of lead 2 chloride are produced. So first, actually, I'm sorry, we need to balance our equation. So we have two NO3s right here. We have one right here. So we're going to put a 2 there. We have now two NAs here and one here. So we're going to put 2 there. Okay, we have 2 CLs here, 2 CLs here. We have 1 PB here. We have 1 PB here. So now we're balanced. Hooray. Okay, so we're going to start our problem. We put our first given over 1. We do our conversion factor, grams NaCl on bottom, moles NaCl on top. 1 next to moles, molar mass next to grams. Grams cancel out. We're left with moles of NaCl. That's not where we want to be. So moles NaCl on bottom. Moles of our product, lead 2 chloride, which is PbCl2. Okay, then moles on top, moles on bottom. So we need our coefficients. 2 for NaCl, 1 for PbCl2. Moles of NaCl cancel out. We are left with moles of PbCl2. That is not where we want to be. So next conversion factor, moles PbCl2, grams PbCl2, 1 next to mole, molar mass next to grams, which is 278.1. Moles cancel out. We're left with grams. That is where we want to be. So now we do our math, and we get 36.4 grams of PbCl2. Okay, so now we do our other given, which is 60.8 grams of not Cl, sorry. NO3. 2. Oh man, I did not leave myself very much room for that. We'll have to repair that up here. There we go. Okay, so grams of that goes on bottom. Moles of that goes on top. One next to moles. Molar mass next to grams. So that's going to be a really big number. 331.22. Oh, there's supposed to be a point there. There we go. Grams cancel out. We're left with moles. That's not where we want to be. So moles of PB, NO32 on bottom. Moles of PbCl2 on top. Moles and moles, so that means that's our molar mass. So that's 1 and 1. Moles of that cancels out. Moles of this does not. So we need moles of this, grams of this, 1 mole, molar mass next to grams. Moles cancel out. We're left with grams. That is where we want to be. And we get for that one 51.04 grams PbCl2. Okay, now, what is the limiting reactant? All right, we first need to identify what our theoretical yield is. Remember, our theoretical yield is the lower of the two. So that is our theoretical yield. Now, oh man, that's a really bad Y. Sorry about that. But you get the idea. Now, the reactant that produces the theoretical yield is the limiting reactant. So that's this one here. So limiting reactant. So our limiting reactant is 15.3 grams of NaCl. And then this bottom question, what is the theoretical yield? We already answered that. That's 36.4 grams PbCl2. Okay, so now we are going to do a percent yield problem. Now, we have determined the percent yield for a reaction between 3.74 grams of Na and excess O2. Now, what that means is we only have one given. We don't have to worry about doing our two stoichiometry problems to figure out our percent yield, or our theoretical yield and limiting reactant and everything. We just have to do one of them because this 5.32 grams of Na2O2, that is not a given. It says that amount of Na2O2 is recovered. That means that is the actual yield. So what that is if we actually did this this experiment, took 3.74 grams of Na and reacted it with O2, 5.32 grams of Na2O2 is how much we gathered after the reaction. Okay, so first things first, we need an equation. Excuse me, an equation. So we have Na and O2. So Na plus O2 yields Na2O2. Okay, now we have to balance it. O's are already balanced. NA's, we have 2 over here. We have 1 over here, so we need a 2 there. And there we go, balanced. Hooray. Next, we do our given. 3.74 grams of Na, and we want to convert that to grams of Na2O2 because that's what it's asking for. Okay, that's our actual yield. So we do our conversion factor. Grams of Na on bottom, moles of Na on top, 1 next to moles, molar mass next to grams. I'm pretty sure that's it. Let me double check and make sure that I am remembering that correctly. Yep. Grams of Na cancel out. We're left with moles of Na. That is not where we want to be. Moles of Na on bottom. We're converting to moles of Na2O2. So that's our mole to mole ratio. Moles of Na is 2. Moles of Na2O2 is 1. Moles cancel out. Moles of Na2O2 is left. Moles of that. Grams of that. And that's going to be our molar mass, which is 78 grams. And 1 mole. Moles cancel out. We're left with grams. We do our math. That turns out to be 6.34 grams of Na2O2. Okay, now that is our theoretical yield. Okay, so to get our percent yield, we need to take our actual yield, and this is our theoretical yield, so I'll mark that. And we need to take our actual yield, 5.32 grams, divided by our theoretical yield, 6.34 grams, times 100. And we get 83.9%. And there's that. All right, next one. If 1 gram of Cu is heated with 1 gram of sulfur, what is the percent yield if 1 gram of Cu2 is obtained? So again, first things first, we need our equation. So Cu reacts with sulfur to form, well, that is a typo. So that is supposed to be Cu2S. At the time of this video, that is still a typo on the review, but I will fix that hopefully as soon as I remember. So that should be an S, not an O. All right, so that should be Cu2S. There we go. All right, now we have to balance. So S's are good. Cu's, we have a Cu2 over here. We have 1 Cu over here, so we put a 2 there, and now we're good. Okay, so our two givens are 1 gram of Cu and 1 gram of sulfur. This is our actual yield. Okay, so 1 gram Cu over 1. We do our grams of Cu. We do moles of Cu on top. Grams of Cu, the molar mass is 63.54. That cancels out. Moles Cu, we are converting to grams of Cu2S. So that is going to be moles of Cu2S. And that's going to be a 1 and a 1 because that's the coefficients. Oh, no, I'm sorry. Should be a 2 for Cu. We keep going. Moles of Cu2S. Grams of Cu2S. 1 in front of moles. Molar mass in front of grams. Moles cancel out. We're left with grams. That's where we want to be. And we get 1.25 grams Cu2S. All right, now we do the same thing for grams of sulfur. 1 gram of sulfur over 1 grams of sulfur, moles of sulfur, 1 mole, molar mass. Grams cancel out. We're left with moles. That's not where we want to be. Moles sulfur, moles Cu2S, 1 mole sulfur, 1 mole Cu2S. Moles sulfur cancel out. Moles Cu2S, grams Cu2S, 159.15. Moles cancel out. We're left with grams, and we get 4.96 grams Cu2S. Okay, so now we have our 2, right? The lower one is our theoretical yield. So that is our theoretical yield. This is our limiting reactant. And this is our actual yield. So we put our actual yield, which is 1 gram, over our theoretical yield, which is 1.25 grams times 100, and we get 80%. And that's our percent yield. Sorry, had a brain fart there. Okay. The last one, the actual yield will be greater than, less than, or equal to the theoretical yield. I'm not going to write this down. I'm just going to talk about it. The actual yield always, always, always is going to be less than the theoretical yield. The reason being is the theoretical yield is the maximum amount of product you can possibly get if there is absolutely no error and 100% efficiency. Okay. Now, actual yield is how much product you actually get if you actually go into the lab and mix the chemicals and collect the product. Now, when you actually do the lab, notice I'm saying actually a lot. That's why it's called actual yield. We are never going to have 100% efficiency. There's always going to be a little bit of error. There's always going to be a little bit of product loss. There's always going to be something that happens so that you don't get 100% yield. Okay, you cannot get higher than the maximum amount possible. That is why the actual yield is less than the theoretical yield. Okay, and that is that. Good luck on your test.